Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 3. Finite Differences and Direct Fit Polynomials. Finite difference formulas can alternatively be derived with the aid of polynomials. A function to be approximated by a polynomial is assumed to be continuous, differentiable, and have exact values at the furnished discrete points. A polynomial approximation can be achieved in a variety of ways, by either directly fitting a set of discrete data to a polynomial or making use of Lagrange polynomials, see Chapter 6, by constructing interpolating functions, or by applying least square fit, see Chapter 7, etc. Follow these steps to create a direct fit polynomial. 1. Establish an nth degree polynomial. 2. Force the polynomial to be equal to fx at n plus 1 data points or nodes, i.e., setting fxi to p sub nxi for all I gives a linear system of n plus 1 equations for a0, a1, a2, through an. 3. Find an approximation to kth derivative at xi for k less than or equal to n by setting it to the kth derivative of p sub nxi. The distribution of xi's depends on the type of difference formulas, forward, backward, or central, to be derived. Once the type of difference formula is decided, the other parameter that we can control is the degree of the approximating polynomial. Deciding on the degree of an approximating polynomial is an important step in this process. Earlier, it was shown that f'(x) computed by the two-point difference formulas, forward difference or backward difference formula, led to first-order accurate approximations, order of accuracy h, while the difference formulas for f'(x), even as order of accuracy h, required 3 points. The truncation error of an nth degree accurate forward difference approximation for f'A is expressed as follows, which implies that if fx is a polynomial of nth degree, the finite difference approximation to any kth derivative, for k less than or equal to n, will be exact since the n plus 1th derivative is 0. This deduction can be used to determine finite difference formulas of the desired order of accuracy, that is, the degree of approximating polynomial. The order of truncation error of a function approximated by an nth degree polynomial is OH to the n plus 1. The order of accuracy of f'x becomes OH to the n. Different relationships for higher-order derivatives apply. For instance, the degree of a direct fit approximating polynomial should be n plus k minus 1 in order to find a finite difference formula of kth derivative with an order of accuracy of OH to the n. Once an approximating polynomial is chosen, assuming the degree of the decided polynomial is n, then it is forced to satisfy n plus 1 data points. This step leads to a system of simultaneous linear equations with n plus 1 unknowns for the coefficients of the polynomial. Then, the kth derivative of fx is approximated by the derivative of the nth degree polynomial. Consider deriving a second-order accurate finite difference formula for the first derivative using a direct fit polynomial. The approximating polynomial for this case should be a parabola. Then, the parabola is forced to pass through the following uniformly spaced 3 data points. We adopt a shifted coordinate system by setting xi equals 0, xi plus 1 equals h, xi plus 2 is equal to 2h. Forcing fx and the parabola to be equal at these points yields the following equations. which is a 3 by 3 system of linear equations, whose solution gives A, B, and C. To find the first and second derivatives at x equals xi, we match the derivatives of fx to the derivatives of the approximating polynomial. Since xi was set to 0, we may also write, which leads to the following difference formulas, where f'(i) and f'(i) are second and first order accurate formulas, respectively. Consider deriving a second-order finite difference formula for the first derivative using a direct fit polynomial. An approximating polynomial should be a parabola. Letting xi equals 0, xi plus 1 equals h1, xi plus 2 equals h1 plus h2. The parabola is forced to pass through the following 3 data points. Adopting shifted coordinate system and setting xi equals 0, xi plus 1 equals h1, xi plus 2 equals h1 plus h2. We match fx and the parabola as follows. Which yields a 3 by 3 system of linear equations. The solution of this system gives the coefficients of the parabola. Next, differentiating the parabola and fx at xi equals 0, we obtain the difference expressions for the first and second derivatives as follows. The truncation error and order of accuracy with the forward and central difference formulations of the first and second derivatives are given as follows. It should be noted that the order of accuracy for the finite difference formula for f'xi is h1 squared plus h1 times h2, which implies that this expression is not truly second order, even though a quadratic fit was obtained. The second derivative has a first order of accuracy, proportional to 2h1 plus h2. The central difference equations for the first and second derivatives are given below. The truncation error and order of accuracy for each equation can be expressed as follows. The order of accuracies of the first and second derivatives are not exactly second order due to varying interval sizes. As h1 becomes closer to h2, the order of accuracy will approach second order. Before the finite difference formulas for non-uniformly spaced datasets are used, the interval sizes must be calculated and saved. Contrary to uniformly spaced discrete functions, the coefficients of finite difference formulas for non-uniformly spaced functions must be calculated for every data point, which increases computational burden. That is all for now. See you next time with another topic. Bye.